All right, hello everyone, and welcome to our first lesson in Unit 8 for the AP Chemistry curriculum. Today we are going to do an introduction into acids and bases, which involve equilibrium proton transfer reactions. We're going to dive into pH and pOH, which is a measure of the concentrations of hydronium and hydroxide ions. We're also going to look into aqueous solutions and how H plus and H3O plus are interchangeable, and then how to use Kw and ion concentrations in different calculations. We are also going to dive into the autoionization of water and all of the calculations that come with that. Thinking back to our introduction to acids and bases in Unit 4, you do need to know the definitions of a Bronsted-Lowry acid and a Bronsted-Lowry base. There are a few different types of definitions of acids and bases, but AP Chemistry uses this one specifically. So with a Bronsted-Lowry acid, that is going to be a proton donor. Remember when I say proton, that is going to be denoted by an H plus. We know that because a neutral atom of hydrogen has one proton and one electron. That plus charge there means that we lost an electron, which means we're only left with a proton. So that is why we use H plus to denote a proton. And then a base is a proton acceptor. Quick overview of conjugate acid-base pairs. Remember, if you were ever asked to write down a conjugate acid-base pair, you have two options. You can either write the acid and the conjugate base, or you can write the base and the conjugate acid. Remember, conjugate acid-base pair is only going to differ by a proton, and that's the easiest way to identify which one is a pair. So if you were looking at this equation on the right here and you were asked to identify a conjugate acid-base pair, you could use NH3 and NH4 plus because they only differ by one hydrogen, or you could use H2O and OH minus. All right, so let's make sure we know how to identify the acid, base, conjugate acid, and conjugate base in an acid-base equation. In my opinion, the easiest way to do this is to identify your conjugate acid-base pairs, which remember only differ by one proton. So starting with NH3, my product that only differs by one proton is going to be NH4 plus. And then I can see, did NH3 donate or accept a proton? And we can see that it accepted a proton because it went from 3 hydrogens to 4 hydrogens. So because it accepted, that means it is the base. And we know that the base turns into the conjugate acid. Now looking at our other acid-base pair, we have H2O and OH minus. We can see that we lost a proton or donated a proton, so this would be our acid, which becomes our conjugate base. Now, if you want to pause the video and attempt the bottom one on your own before I explain it, that would be great. So our first conjugate acid-base pair is HCl and Cl minus, because we can see they only differ by one proton. That is going to donate the proton because we started with one hydrogen and now we have none. So because we're donating, that would be an acid. And remember, the acid becomes the conjugate base. And then our other conjugate acid-base pair is H2O and H3O plus. We can see that it accepted a hydrogen, so that's going to be a base. And that's going to turn into a conjugate acid. Now looking at these two specific acid-base reactions, you can see that water acted as an acid in the first equation and as a base in the second equation, and that is something called an amphoteric substance, something that can neutralize an acid and neutralize a base. Something a little more specific than that is something we call amphiprotic. That definition is a substance that can either accept or donate a proton, which water can do. So water is both amphoteric and amphiprotic. All right, so this is a very important slide. I know I already taught you how to memorize the strong acids and strong bases, but we are going to go over it again because if you do not know these, you are going to struggle in Unit 8 when you are going through the actual AP chemistry exam. So with our strong acids, we have 3 directly from the periodic table. That's going to include chlorine, bromine, and iodine. And then we have 4 that involve our polyatomic ions. I will say that HClO3 is not always used in AP Chemistry as a strong acid, but I have seen it in some scenarios, so I do include it when we are going over the memorization of strong acids. And then for our strong bases, we have 5 from group 1 metals. So since they're group 1 metals, they have a positive 1 charge, so we only need 1 hydroxide. And then we have 3 from our group 2 metals, which is why they need 2 hydroxides attached to that cation. And just remember that when we are talking about strong acids and strong bases, that means that they completely dissociate into ions when put into water. So for example, if you have 10 moles of HCl and you put that in water, now you're going to have 10 moles of H plus ions and 10 moles of Cl minus ions. All of those molecules are going to separate into ions. Same with the bases. If I have 5 moles of lithium hydroxide and I dissolve that into water, that means I'm going to have 5 lithium ions and 5 hydroxide ions. So that just means complete dissociation 100%, and that is very important when we're talking about strong acids and strong bases. Now, when you get your periodic table on your final exam, I do recommend doing a few things on the periodic table. The first one is identifying your strong acids and your strong bases. So starting with the bases, they actually make a lowercase b on the periodic table. So if you want to just take your pencil or whatever you're using and make a B on the periodic table, those are your H strong bases. You just have to attach the hydroxides to them. Then for your acids, you have 3 from the periodic table. They're all right next to each other. So you have Cl, Br, and I. My students like to say Cl-Br. So for your strong acids, you'll have HCl, HBr, and HI. And then you have the 4 from your polyatomic ions. And the way that I have my students remember this is clo, no, so, 3, 4, 3, 4. And then you have to add your hydrogens. Just remember that SO4 is a 2 minus charge, so you need 2 hydrogens on that one. So clo, no, so, 3, 4, 3, 4 is our little jingle to remember those specific strong acids. So these are the 7 strong acids that you do have to memorize, and I do recommend putting that on your periodic table when you get it. And then remember your strong bases, you just attach the hydroxide. So for example, LiOH, NaOH, KOH, RbOH, CSOH, and then for your group 2s, you'll just need 2 of them. So CaOH2, SrOH2, and BaOH2. And if you are given an acid or base that is not one of these, then you can assume that it's weak, and you'll have to do different types of calculations for that. All right, so now what I want us to do is to visualize what this actually looks like at the particle level. So remember, for strong acids and bases, everything dissociates. So when you are drawing at the particle level, you should only see ions in solutions and no molecule should be left intact. So let's go ahead and start with HCl. Let's say we have 4 moles of HCl, and I want you to draw the dissociated particle model of what that looks like. So if we have 4 moles of HCl, that means we have 4 H plus ions, And that also means we have 4 Cl- ions. Now for our NaOH, let's do the same. Let's say we have 4 NaOH molecules. That means we now have 4 Na pluses. And 4 OH minuses. And then for our weak acids and bases, those only partially dissociate. So if you have to draw a particle diagram, you're going to draw a mixture of ions and undissociated molecules. So again, let's go ahead and say we have 4 moles of HF. I'm going to just kind of assume that 3 of them are going to stay together. So I have and then 1 H plus by itself. And then we're going to have 3 fluorines still together on the hydrogen, and then 1 fluoride ion by itself. So you can see at the particle level that 3 out of the 4 molecules are still together, not dissociated, and then we have 1 that is dissociated into the constituent ions. Let's go ahead and do the same thing. NH3, say we have 4 molecules. We're going to dissociate 2 or 1 of them. I don't think it really matters as long as you show that some of them are dissociated and some of them are not. But I'm going to stick with the same. So we're going to have 3 together. Right, and that's what that would look like at the particle level. So we have 3 NH3 molecules still together, and then we have 1 that has separated into ions, and this one is not fully written because it doesn't have the states of matter, but technically there would be water as well. And that's where the OH comes from. So key takeaway, strong acid and base means fully dissociated. Weak acid or base means partially dissociated. So now let's connect this to what happens in pure water. So water can actually react with itself in a process that we call autoionization. And that's where one water molecule donates a proton and acts as an acid, and another water molecule accepts it and acts as a base. And that is going to produce a hydronium ion, which is H3O+, and hydroxide, which is OH-. And that is why even pure water has both ions present, because it does partially dissociate into those ions. In this unit, you're going to hear us say a lot that H3O plus is equal to H plus. And the reason that it's equal to each other is because of what's actually happening at the particle level. So when we have water ionizing, what's actually happening is that liquid water breaks apart into H plus and OH minus. However, this H plus or proton is so small and so reactive that it's not going to last and you're not going to be able to actually have H plus by itself in solution. So what happens is that proton binds to a water molecule and produces H3O plus. So while this is technically the ionization of water, this top equation is much more accurate because this proton does not last long and binds to another water to make H3O plus, which is why we needed 2 water molecules in this top equation. And another reason why you can use both H3O plus and H plus is when you're looking at these 2 different equations for the autoionization of water. If you make Kw, remember Kw is an equilibrium constant. When we're doing an equilibrium constant, it's products over reactants, but pure liquids are not included. So looking at these 2 equations, we have H3O plus times OH minus and nothing in the denominator, again, because this is a liquid and it's not included. Same goes for the bottom equation. We have H plus and we have OH minus. So their equilibrium constant expressions are pretty much the same, just switching out H plus and H3O plus. And both of those are equal to 1 times 10 to the negative 14th. So this is why we can use those 2 interchangeably in our equations. Now we go through the majority of our childhood learning that water is neutral and has a pH of 7. However, that is only a true statement at 25 degrees Celsius. If you change the temperature of water, then you are going to change the pH of water. And to understand that, we need to go back to Le Chatelier's principle, which we learned about in Unit 7. So looking at the autoionization of water, we can see that liquid water is being broken apart into its constituent ions. And we know in order to break bonds, we have to put energy in. And when energy is put in, that means we have an endothermic reaction. So if we're looking at this equation and we know it's endothermic, we talked about the heat being a reactant. So if we increase the temperature of water, we are going to shift away from the heat, which means we are making more ions. And because our concentration of H plus and OH minus are the same, they're both going to increase. And because we have more hydronium, we are actually lowering the pH. So by increasing the temperature, we are lowering the pH of water, which is making it more acidic. And same going the opposite direction. If we decrease temperature, then we are increasing the pH, making it more basic. So looking at this pH scale, remember that pH measures the concentration of hydrogen ions. And if you wanted to solve for pH using the concentration of hydrogen ions, just remember the equation is pH is equal to the negative log of the concentration of H plus or H3O plus ions. And this pH scale is logarithmic, which means each step is going to be a 10 times change. Now, when we're at neutral pH of 7, that is when the concentration of H plus and OH minus ions are the same. You can think back to water. No matter what temperature our water is at, the concentration of H plus and OH minus are going to be the same because water is always neutral. That doesn't mean it always has a pH of 7, but water is always neutral. Then we go looking at acids and bases on the pH scale. Acids are going to have a lower pH, less than 7, with a higher concentration of H plus ions. Remember, the lower the pH, the stronger the acid. So if we're looking at 2 acids, one with a pH of 5 and one with a pH of 1, that pH of 1 is going to be a lot stronger of an acid. And then with our bases, those are going to have a higher pH greater than 7 with a higher concentration of OH minus ions. Remember, the higher the pH, the stronger the base. So if we're looking at a base with a pH of 13, versus a base with a pH of 10, that pH 13 is going to be much stronger of a base than the other. All right, so now that we understand the basics of what is happening at the particle level, let's apply that with some math. So on the right is our equilibrium box of our reference sheet. You're going to have a lot of different equations here that you will use on your exam. Remember, when you're doing any sort of calculations with acids and bases, that H plus and H3O plus are interchangeable. So if you see them on your reference sheet and you're like, oh shoot, I have H plus concentration, that's the same thing. So you can just plug that in instead of H3O plus. So if you are given concentration of an ion, either H plus, H3O plus, or OH minus, then you can use our equations here to solve for pH or pOH. So it's essentially just going to be taking the negative log of that concentration, and that's going to give you pH or pOH. Remember, if you are given concentration of hydroxide ions, but you want to solve for pH, first you're going to take the negative log of that to get pOH. Then you're going to take 14 and subtract your pOH, and that's going to give you your pH. So just remember, this equation is also going to help you kind of change over from pH to pOH. And then going the opposite direction, if you are trying to get concentration of ions, but you're given pH or pOH, you just put 10 to the negative pH or 10 to the negative pOH, and that will give you your concentration of your ions. All right, let's dive into some practice problems. Number 1 says, what is the concentration of H3O plus in a solution of pH equals 2.876? So I am given pH, and I want to find my concentration of H3O plus. And I know if I want to find concentration and I'm given pH, I'm just going to have 10 to the negative pH. And because I am given pH, I can put in my calculator 10 to the negative 2.876, and that will give me my concentration of hydronium ions. That gives us 0.001330, and converted into scientific notation, that would be 1.330 times 10 to the negative third, and that's our concentration of H3O plus. All right, let's look into the second example. What is the molarity or concentration of OH minus in a solution of pH equals 8.9? So because I want to solve for concentration of OH minus, I should be in pOH. So my first step is to get pOH from pH. And to do that, I'm going to take 14 minus the pH, and that gives me pOH. So 14 minus 8.9 is going to give me 5.1 for my pOH. So now that I have my pOH, I can go ahead and solve for my concentration of hydroxide ions by taking 10 to the negative pOH. And that gives me 7.94 times 10 to the negative 6 for my concentration of OH minus ions. And then for number 3, what is the concentration of OH minus in a solution with H3O plus equals 3.76 times 10 to the negative 5th? So I know that the concentration of OH minus times the concentration of H3O plus is going to equal my constant, which is 1 times 10 to the negative 14th. And because I know my concentration of H3O plus, I can just plug that into the equation and solve for OH minus. So to do that in my calculator, I will put 1 times 10 to the negative 14th divided by 3.76 times 10 to the negative 5th. And that will give me 2.66 times 10 to the negative 10th. And that's going to be my concentration of OH minus ions. All right, so now that we've done a few together, I would love for you to pause this video and try to fill in all the boxes on this table on your own, and then press play when you want to get the answers. So first, in order to find my concentration of H plus or H3O plus ions, and I'm given pH, I'm just going to have 10 to the negative pH, which is 3.78. So plug that into your calculator and then get the answer. For pOH, I'm just going to take 14 and subtract my pH, which is 3.78, and that will give me my pOH. And then to get my concentration of OH minus, I'm just going to do 10 to the negative pOH. And because we are given a pH of 3.78, I know that's very acidic, so this is going to be an acid. All right, and here you have your answers for that first row. I want you to take a quick look at this pOH given here. When we are doing sig figs for acids and bases, the rule is slightly different, so we're not focusing on the number of sig figs given to us. We are actually looking at the number of places we go after the decimal point. So since we are given a pH into the hundredths place, we're going to always answer in the hundredths place. So you can see all of my answer choices are going to include 2 numbers after the decimal point. Now, I've never really seen this marked off in the mark scheme, but this is technically how you do it for acids and bases. If you want to just follow our normal sig fig rule, I don't see it hurting you too much, but this is technically the rule. All right, so in our next row, we are given the concentration of H plus or H3O plus, and we need to fill everything else in. So in order to get pH, when I'm given H3O plus, I'm just going to take the negative log of my concentration. So 3.89 times 10 to the negative 4. So put that into your calculator and that will give you your answer. To get pOH, remember I'm just going to take 14 and subtract my pH that I just got. And then to get my concentration of OH minus, I'm just going to do 10 to the negative pOH. Now, to identify whether it's an acid or base, I always look back at the pH. Because I have a pH of 3.41, that is going to be acidic. So those are your answers for the second row. Now looking at the third row, we are given pOH. So from there, we can get the concentration of OH minus ions by taking 10 to the negative 5.19. We can also get pH pretty easily by taking 14 and subtracting 5.19. That will give us our pH. And then to solve for a concentration of H plus or H3O plus ions, we're just going to take 10 to the negative whatever you get for pH. And again, looking at our pH, we can see that it is 8.81, which is above 7, which means this is a basic solution. And then in this final row here, we have a concentration of OH minus given to us. So in order to get pOH, we're going to take the negative log of our concentration of OH minus, which is 4.88 times 10 to the negative 6. Then when I get my pOH, I can take 14, subtract my pOH, and then I will have my pH. And then I can take 10 to the negative pH to get my concentration of H plus or H3O plus ions. And when we do those calculations, we end up getting a pH of 8.69, which is above 7, so that's going to give us a basic solution. All right, to wrap up this lesson, let's check your understanding with a series of true or false questions. I would love for you to pause before I give the answer to each of these to try to write down what you would answer in an FRQ and then check your work. So the first one says, a sample of pure water has a pH of 7 at any temperature. So that statement is indeed false. If that statement said a sample of pure water is neutral at any temperature, then it would be a correct statement. But the fact that it says it always has a pH of 7 is false. So pure water is always neutral because the concentration of H3O plus is always equal to the concentration of OH minus. However, that doesn't mean the pH is always the same. So if we have a pH of 7, that means our water is at 25 degrees Celsius. If we change that temperature in any way, then our pH is going to change. Remember, our equilibrium constant of the auto ionization of water is going to change based on temperature because of Le Chatelier's principle. So because it's an endothermic reaction, if we increase that temperature, it's going to shift towards the products or the ions. And having more H3O plus in solution is going to decrease our pH. So changing the temperature does change the pH of water. Next statement, the concentration of H plus and the concentration of OH minus is equal in a sample of pure water at any temperature. That is a true statement. So in pure water, autoionization always produces equal amounts of H plus and OH minus, so their concentrations are equal at any temperature. However, just keep in mind that their actual values or the pH can change with temperature. They'll still be equal to each other, but they will change the pH. Next one, a sample of pure water is neutral in which pH equals pOH. That is a true statement. So a solution is neutral when the concentration of hydronium and hydroxide are the same, which means pH is equal to pOH. So for example, if you take water and you increase the temperature, you're going to decrease your pH. So let's say you have a pH of now 5.9. That means you're also going to have a pOH of 5.9. If the pH of a sample of pure water is less than 7, then the temperature of the sample must be less than 25 degrees Celsius. That is a false statement. If we are having a pH less than 7, that means we increase the temperature. So it would have to be greater than 25 degrees Celsius. Our next one says H2O ionizes to a greater extent at 50 degrees Celsius than it does at 25 degrees Celsius. And that is a correct statement because remember with our equation, 2H2O reacts to form H3O plus and OH minus. If you have an endothermic reaction and your heat is a reactant, when you increase the temperature, you want to go away from the heat. So we are making more products, which means we are having more ions, so greater ionization. And then our final example for this lesson, if a sample of pure water has a pH of 6.8, then the pOH of pure water must be 7.2. And that statement would be false. If you had a pure sample of water with a pH of 6.8, then your pOH will also be 6.8. And since we have a lower pH, that means we increase the temperature of the water.